In episode 1, we established a relationship between electromagnetism and gravitational acceleration, utilizing the Buckingham pi method. Specifically, we found the ideal solution for any transverse electromagnetic plane wave, in the context of Maxwell's equations. This means that a classical transverse electromagnetic plane wave can mimic gravitational acceleration, without any relationship to the Lorentz force, if, and only if, it possesses sufficient amplitude and frequency. This conclusion is standard general relativity. It is well known and understood that depositing sufficient energy of any form into a small space will measurably curve spacetime. We may classify this as the first step towards spacetime engineering. However, the problem we now have is that our episode 1 solution produces a wave, but we need a constant. We do not experience gravitational acceleration as an oscillating phenomena. So, how can we transform a time-varying solution into a constant? Actually, this is an extremely easy outcome to achieve and has been known to standard physics for hundreds of years. It involves the principle of superposition, in Fourier harmonics. Therefore, in this episode, we're going to demonstrate the quantization of gravitational acceleration by combining our Buckingham pi result from episode 1, with Fourier harmonics. What does our ideal solution, in the context of Maxwell's equations, physically mean? Here we see the unification of experimental relationship functions, from episode 1. This unification applies specifically to transverse electromagnetic plane waves. Experimental relationship functions describe the similarity between the mathematical model and physical reality. If gravitational acceleration were an oscillating phenomena, the similarity to our experimental relationship functions would be 100%. Hence, they would all take the value of unity. However, a sine wave is clearly not very similar to a constant function, so our challenge becomes: how do we transform an oscillating input into a constant output? That is, how do we ensure that all of our experimental relationship functions equal 1? Thus far, we have demonstrated that the unified experimental relationship functions shown are a measure of similarity between the mathematical model and physical reality. When any mathematical construct represents physical reality perfectly, the value of the associated experimental relationship function is unity. So, how can we build the required value of unity from electromagnetic waves? Answer: adding electromagnetic waves together. This is termed superposition. Each specific wave is represented by its own k function. When we add the k functions together, we get the overall k function, appearing as output on the illustration. On the left-hand side, we see waves which have been added when they're in phase. On the right-hand side we see waves which have been added out of phase 180 degrees. However, the output on the right-hand side is 0 and therefore, unusable. So, what is the key takeaway from this illustration? The superposition principle is on the right track, but we need to limit ourselves to a final solution where all waves, to be added together, are in phase. Well, does an off-the-shelf solution exist for us to use? Fortunately, it does. Let's take a closer look. On the right-hand side of this frame, you can see multiple examples of how it's possible to construct functional solutions utilizing Fourier harmonics. This is not a new technique. It has existed for centuries and was developed by one of the greatest minds in the history of our species, Joseph Fourier. On the left-hand side, you see a graphical representation of the number 1, constructed utilizing Fourier harmonics in complex form. This is termed the unit harmonic operator. In our case, the number of terms plotted is n plus 1, where n equals 11. Hence, the number of terms plotted is 12. This means that the graph you're seeing was plotted by adding the first 12 harmonics. Because the harmonic distribution is double-sided and odd, the harmonics plotted are written on the illustration as negative and positive modes. Moreover, it's important to note that the unit harmonic operator is represented in complex form. Consequently, all imaginary terms sum to 0. Only the real terms remain. The unit harmonic operator is embedded with two spectra, an amplitude spectrum and a frequency spectrum. the magnitude of the amplitude spectrum decreases asymptotically to zero and the magnitude of the frequency spectrum increases linearly to infinity. Now that we have defined and described the unit harmonic operator as developed via the electrogravimagnetic construct, let's look at the key takeaway. Most importantly within this frame, is to note that the experimental relationship function equals the unit harmonic operator. This occurs as the magnitude of the harmonic mode limit tends to positive infinity. Therefore, we have demonstrated that 100% similarity between a natural and artificial gravitational acceleration field may be achieved via the principle of superposition, if, and only if, the artificial gravitational acceleration field is constructed utilizing transverse electromagnetic plane waves, and applied via a method of construction obeying a Fourier distribution. Let's now take a look at what we can achieve with this mathematical fact. The previous slide begs the question: why a Fourier distribution? What makes this kind of distribution so significant? The answer is that it's the most efficient numerical summation solution possible, in order to achieve the required outcome. Any other distribution representing the superposition of transverse electromagnetic plane waves is less efficient because it does not constitute the lowest possible energy condition. Utilizing the unit harmonic operator, we may define two additional forms. But first, let's recall that all imaginary terms sum to zero and only the real terms remain. Mathematically, we can prove this according to the integrals shown. You can clearly see that the average value of all real terms over an arbitrary period is unity, and similarly, the average value of all imaginary terms over the same period is zero. Thus, we may define the massive and gravitational harmonic operators, and consequently, a table of amplitude and frequency spectra may be formulated. Therefore, we may achieve our objective of quantizing gravitational acceleration by expressing the gravitational harmonic operator in terms of an experimental relationship function utilizing transverse electromagnetic plane waves, as described by Buckingham pi theory. Let's now have a look at what we've been able to achieve in this presentation. Firstly, we utilized the experimental relationship function derived in the first episode, to find an ideal solution utilizing Fourier harmonics. Next, we introduced the concept of a unit harmonic operator and established that it equals the required experimental relationship function, as the magnitude of the harmonic mode limit tends to positive infinity. Consequently, we established the concepts of massive and gravitational harmonic operators. This enabled us to quantize Newtonian gravity over the Fourier domain, utilizing the principle of superposition applied to transverse electromagnetic plane waves. So, what can we conclude from our analysis? 1. Superimposing a sufficiently large population of transverse electromagnetic plane waves, obeying a Fourier distribution, yields an artificial gravitational acceleration field which is dynamically, kinematically and geometrically similar to a natural gravitational acceleration field. 2. A natural gravitational acceleration field may be modeled as a spectrum of transverse electromagnetic plane waves obeying a Fourier distribution. 3. Newtonian gravity has been quantized over the Fourier domain.